cannot go for that. You know, it's a matter of comparing ante-mortem and post-mortem information. And in some cases, you have a very short amount of ante-mortem information. There is a first step on profiling to look for the candidates, and then it's usually manual comparisons and the final decision. So we try to automate some of these approaches using AI, different AI techniques. So this is not, from our viewpoint, it's research, but it's not the typical thing of the hammer. You have a hammer, a technique, and you want to apply it. So we are open along these 20 years to use the most specific technique we can use to solve it. So some of you already visited our scanners lab yesterday, our AI for Human ID lab. This is also Inma Lehmann's lab. Those are, I don't have time, but I like this picture because those are Christopher Columbus bones. So I always say that, tell the story if somebody wants to know about it. We have the coffee break later. And we started with some AI applications to medical imaging. So automatic segmentation of bone structure. And you know this guy. Automatic medical image registration. So we translate for this fixed environment where it's so easy, let's say, because you have a control environment with all of the parameters, to an open environment where we have to estimate the right parameters in order to apply the techniques. So I'm not stopping at all of craniofacial superimposition. You know more than me. This is another funny game we do with a real world case, and Inma Lehmann that is underneath that second superimposition to show non-experts that the improper skull doesn't match the right one. And you know, usually there are 4 steps. So our idea in 2005 was to try to automate craniofacial superimposition in order to help the forensic anthropology. That's what you see, the starting of what you see yesterday in skeletal ID. So that was the usual approach they were applying. By that time, they were already using 3D scanners here in Granada. And we helped them with the 3D model reconstruction. We applied 3D to 2D image registration in order to superimpose the skull over the face. And we also, that's something new you haven't seen in skeleton ID, we also help in the final decision. Yesterday, Alejandra gave a nice talk on the 4 different families of criteria. We implemented some of these criteria, automated them, and aggregated the info in order to get the value between 0 and 1, to provide some specific approach to the technique in order to do it applicable. So this is the first stage. I always have my mobile phone here. So if I take a picture of all of you, you know you are a 3D scene, and I'm getting a 2D projection of this 3D scene. So when you get an ante-mortem photo of the subject, you don't know where it was taken, which picture, with which camera, sorry. So if you haven't got metadata, you need to guess the right position. So we look for the most natural approach. So this is the original picture, and that's the scene it had. We make the 3D model of the skull, and using evolutionary algorithm, one of those heuristic searches, we put the skull in the position it was supposed to be in order to be projected. But we don't know the length, we don't know the distance. Pablo will show you how to estimate the distance using different approaches and so on. We thought that was the most natural approach, and it worked. And Inma said, she never said it again, but at the beginning, she told us that in some cases, they took 8 hours in order to make a superimposition, a manual superimposition, working with Photoshop and with the 3D skull. And this takes 2 to 4 minutes, and then Andrea came and made it in seconds. So in the skeleton ID you saw, it's made in seconds. So we started to add some additional approaches. As I told you, it's an uncontrolled environment. We don't have the information. We had lack of information. You know, it's so difficult in some cases to locate the landmarks. This is something that is not in a skeleton ID, but at the beginning we provide the forensic anthropology, we provide the expert with the chance of not marking the specific undoubtedly point landmark, but to use a region. For example, for the vertex, it's so useful. And we model that using AI in order to measure the distances. And yesterday you saw the cones with Alejandra. So not only for the final evaluation, we also incorporated these cones in the projection, in the registration, in order to check the distances to try to provide additional information for the registration. And yesterday you also saw the mandible. It's a second object. That was the PhD dissertation by Enrique Bermejo that is around. So we try to provide all the possible uncertainty sources and cover them in order to get a better registration. And finally, it works in that way. And the last part before giving the floor to Pablo, for the last stage, we also provided a kind of systematization. So taking the information from MEPROX with the different criterion, with the final decision from MEPROX, you saw yesterday in the workshop, there are usually 4 different family of criteria. I'm not going to stop into that, but you will see Oscar Ibáñez again. What we did was to model 9 different criteria using image processing techniques. And then it can compute a value, a degree of matching. And then we designed a hierarchical approach, explainable in order to provide a final report as the one you saw in Skeleton ID yesterday, where you start from different skull face overlays. For each of them, you look for different regions, different criteria. For each of them, you apply different image processing techniques, and you aggregate from bottom to up all those values in order to get a final value between 0 and 1. And something that Caroline also asked yesterday, the quality of the material. So we also added here in this aggregation, your expert opinion saying this photo is a low quality photo, so you need to reduce the trust in the system, in the final decision. This skull is damaged, so it has less information than the other. Finally, it's aggregated to take a degree of support between 0 and 1. And in order to tune the system, we use machine learning approaches. So we use a training and a test system in order to tune the system to work. So I'm not stopping at the skeleton ID. You were playing with it yesterday, just to finish with some validation approaches. This was because, you know, this is so nice and I can tell it, but if it doesn't work, we are not going to use it. This was a study that was done at the MEPROX European project. And there was a comparison, a blind test, 60 cases with 26 forensic experts from different international labs, each of them working, doing craniofacial superposition with their own means, not against. The automatic system was one more of the approaches, right? And finally, this was the mean of all the 27 experts, well, the 26 plus the automatic system, 79% of accuracy, following the MEPROX guidelines. The best expert got a 93%, and the automatic system was the second one in the study, with a 90%. So not that bad. And you know this case. It's a work that Panacea has done with the skeleton ID in Vilna. It's an historical memory case. It's a very difficult case because there is one picture for some of the skulls. The forensic anthropologists in Granada and in Panacea working with the case didn't have access to the material, so they were scanned there and sent here. And finally, they got close to 100% of accuracy. And this has been used for 20 years in the judging space. So in some historical memory cases, in several cases of migration, murders, suicides, accidents, and so on, forensics by Granada, and now Inma Alemán and Fernando Navarro are working on that, Panacea's forensic experts. And I have some recent cases for you on migration. I have the right to show them. I was taking it. So this is a very interesting case of migration. You know, Spain is a migratory place from Africa, so we are trying to collaborate with international Red Cross and so on. And those cases are taken directly from the judge to the Institute of Legal Medicine, and then move to the forensic lab by INMA, directed by INMA. So that was one of those cases. And in this case, they had 2 candidates, 2 brothers. So usually these guys and these girls, before leaving, before taking the patera, before taking the small ships they are using, they made photos to themselves. So in some cases, you have the ID photos, and in some cases, you have some more. So here, the problem is that, as you know, DNA cannot be used to individualize 2 brothers. So craniofacial identification was used and accepted by the judge in order to recognize one of them. And This is another case from another migrant, so another sad case, and that was pictures from the social media, from the social network of the person. So it was identified using non-usual pictures, as you can see, not the typical frontal pictures, using several of them, complementing the evidences and so on. And I don't know how long I've been, probably more than expected. Well, 25 minutes. So we are still on time with our plans.
Can you hear me? Yeah. Well, first of all, thank you for the invitation. I'm very happy to be here giving this talk. Thanks a lot for the organization of this very nice event. And of course, thanks to all the attendees in person and online. Well, how does this work? Yeah. So, well, I'm going to talk a bit about some, I don't know if call them advanced methods, but in any case, these are some contributions that we have been doing for the last years on automatic craniofacial superimposition. And as you know, as Oscar said, well, there are 4 main stages in craniofacial superimposition. Stage 1, acquisition and processing of antemortem and postmortem materials. Stage 2, face and skull examination. Stage 3, skull face overlay. And stage 4, decision making. What you can see in red in this slide are, well, we are trying to contribute in all of these stages, but in this talk, I'm going to focus on our contributions on stage 1 and stage 3. In stage 1, we try to move from manually locating the landmarks to automatically locating 2D landmarks and 3D landmarks. And on stage 3, what we want is to try to estimate automatically subject to camera distance and facial soft tissue depth. With respect to the first project, the automatic localization of cephalometric landmarks, well, since we don't have much time and I wouldn't like to give so many details, I'm going to focus mainly on the intuitions. What we are going to use is machine learning. As Oscar said, when you want a machine to learn, the only thing you need, of course, you need a learning algorithm, but the most important part are the training data. But in forensic anthropology, you have many times not many examples. So in this case, it's important to give credit to the PhD student who developed this work, Guillermo Gómez Trenado. I don't want to miss the opportunity to congratulate him because in 2 weeks, he's going to defend his PhD. And in his work, he was thinking, okay, I want to solve this problem. You can see again, I think at this point you are very familiar with this guy. So you have this input image, and I want to automatically locate all these facial landmarks, all these cephalometric landmarks in here. How can I do this if I don't have many images? In this case, 165. So he came with this nice idea of using an initial localization. You can see here, this is the full pipeline of this work. And even in your, at least for you to have this, this knowledge about this way of working, but also to give you the information that this is a way in which when you work in machine learning, this is quite common. You use pre-trained models. What is a pre-trained model? A pre-trained model is a model that has been trained, even if it's not exactly the same task. It's a task which is quite similar to the task you want to solve. And you are able, or somebody with the GPU servers is able to train this model with thousands, hundreds of thousands, millions of images. So what he did was to train, to use a pre-trained deformable 3D mask model, like you can see here in step 1. This deformable model is going to suggest a reliable initial landmark localization that you can see here in step 2. And then you use a refining process. You are going to see this also in the next project, as well. So you are going to work with cropped images around the initially located landmarks, and you are going to train a deep network, but let's say smaller than the initial one, that is trained to predict the displacement in order to correct these initial positions. And to do so, we use just a single network that receives as input this crop, the crop image for each landmark. This is conditioned by the landmark, and the result is these vectors that you can see here that you can add to the initial location in order to refine the position. This is the main intuition. We perform a user study. 6 forensic experts were presented with 2 landmark annotation locations for comparison. The one automatic from the method presented before, developed, as I said, by Guillermo Gómez Trenado, and then a human expert. And we saw that this model is equal or better than the human expert in around half cases. So we could say that either we could say that this is competitive with experts, or at least we could say that this is a nice tool to an initial localization of points that later can be refined or reviewed by an expert, by a human expert. And then we were also predicting the visibility of these landmarks. So given the image with the landmarks, what landmarks are visible or not, and we had an accuracy of 83% using just a pure geometric approach. And when using deep learning in one of the last works related with this line, Carlos Lara, whose work was supervised by Guillermo, by myself, and Javier Merí, another researcher from the University of Granada, we are able to increase this accuracy to 85%. This is with respect to cephalometric landmarks. If we move to craniometric landmarks, we were working, and the main leader of this research line is Enrique Bermejo, that you may know as well. So in this case, we use a different approach, more related with 3D computer vision, where we have a database of skulls. Well, I didn't say that we were trying to automatically locate 58 craniometric landmarks in these 3D models. From this database, you are able to create an average template. So you have, we create a somewhat representative skull, an average skull from this database. We have annotated this average template. So once we have a new target model, a new skull, we can overlap, we can superimpose in some way both, deforming the template to fit the target. And once we have this registration, we have an initial location of the landmarks. Because since in the average template we have the landmarks located, when we deform this template to fit the target model, then we have the position of the landmarks. Once we have this initial localization of the craniometric landmarks, what we do is a local refinement, an ad hoc local refinement with a particular strategy for each landmark. And the error we got is around 2 millimeters as average localization error, that we could say that may be competitive as well with human experts. So in any case, either if we want to use this tool and the previous one to automatically localize landmarks, or if we want to use them as initializer, a tool to get an initial localization of points that later can be refined, we could say in any case that these are useful tools, as artificial intelligence is. Artificial intelligence are just tools to help humans to develop some work, and this can save us time. Then also with Enrique Bermejo and Enrique Fernandez, we were working on the estimation of subject to camera distance. If you are not aware with this concept, well, it's the actual distance between the camera and the subject, and the same as camera position, camera orientation, focal length, and so on, it can be considered, it's considered a camera parameter. So as Stefan and Armstrong wrote in 2021, subject to camera distance is widely acknowledged to be a critical variable in craniofacial superimposition, but in practice, it has been notoriously difficult to estimate from facial photographs. We try to contribute a little bit here. We use deep learning in a way that I'm going to explain in the next slide. But just for you to know that this subject to camera distance affects face configuration and perceived identity. So why it can be useful to estimate as in a way as accurate as possible this SCD? Because if we know the SCD, we can determine the degree of distortion, because perspective distortion, as you can see in this example, is larger at shorter distances. And then we can improve the accuracy of computer-aided recognition tools, or we can increase the reliability of human identification. So what we did here, so in this research, as I said, developed mainly by Enrique Bermejo, we were working with 3D models of complete full pose, complete bodies, or 3D models of faces. And then again, as I was saying before, if you want to use machine learning, what you need is data, okay? For instance, this is something I was teaching, this is something I say to my students in machine learning. Even if you have a mathematical expression that is able, that solves your problem, you can use machine learning. Maybe it doesn't make much sense, right? Because you have a closed form expression to solve a problem, but you can use it. Even if the pattern you're trying to learn is random, completely random, you can use machine learning. What you are going to learn is a random distribution, but you can use it. But you cannot use machine learning if you don't have data. So in here, we were generating synthetic images from these 3D models. We were combining different backgrounds. And then we use training data for different focal lengths at different distances. We use a learning algorithm to learn from this training data. And now we can use this trained machine to estimate the subject to camera distance from an. So some results to go directly to the point. So we created a novel synthetic data set of facial photographs taken at several distances, and we were using deep learning-based methods, creating a model for different focal lengths, 27 millimeters, 35, 53, and 83.6. And our results, we could say, even if these are preliminary results, even if these are just promising results, we could say that they are competitive with state-of-the-art results like Perspective X and Google Iris. We were using a test set of real images, more than 1,000 real images with 29 different distances, aging from 50 centimeters to 5 meters, and using a focal length of 35 millimeters. And our median mean absolute error was about 8 centimeters, 8.7. And the median mean relative error was about 6.7%. So this means that if the distance is 100 centimeters, the median error you are making is around 6.7 centimeters. And this is a quite interesting result from my point of view. Our current need real images for fine-tuning. Fine-tuning means that when you use, do you remember what I was saying before about pre-trained models? You have a pre-trained model, which is a model trained on millions of examples. And then fine-tuning is the process of adjusting a little bit the weights of your model in order to be able to solve your particular problem, the particular problem you are interested in. So for fine-tuning, we didn't need real images, and we were using just simulated data. And these are our last results by Ivan Salinas, a student supervised by Enrique Bermejo and myself. Well, as you can see, well, this is the graph with the target distances and the predictions. Something interesting is that we have smaller errors at shorter distances, which is exactly where perspective distortion will accumulate. So as I'm saying here, we are interested in having an accurate prediction at this distance, right? I mean, we have a lot of margin for improvement, but in any case, this is also a contribution from artificial intelligence to this problem. Now, we were working as well with facial soft tissue depth estimation. As you know, well, this is of particular interest in craniofacial identification, and it can be used to estimate the position of facial landmarks from the corresponding landmarks on the skull. Usually, at least as far as I know, the average distance from a population is used, and we were saying, okay, so why not to try to particularize to each subject, in the sense that we can learn from a population and maybe given some craniometric landmarks, try to estimate the position of the facial landmarks, or in this case, to estimate the facial soft tissue depth. So the input to our machine learning model will be the craniometric landmarks, which are these blue dots here on the skull. And well, we can include, of course, other information like age, sex, or body mass index, and the output will be the facial soft tissue depth per landmark. which is what we are trying to do, and this is why I'm showing this slide. We are trying to predict like the radius of this sphere around the craniometric landmarks. So at this point, we are not paying attention to the direction. Materials and methods we use. So we were using 500 examples taken from this research paper, 253 landmarks plus sex and age. We have the 3D positions of all these landmarks, and we have many missing values, around 37% of all data missing. And in these kind of situations, it's quite interesting to use what are called imputation methods. So it's like creating, interpolating, extrapolating points from the data set you have. So we were using different machine learning models like support vector regression, which is the extension to regression of support vector machines that are were designed for binary classification, partial least squares, which is an extension of linear regression, multi-layer perceptron, a neural network, k-nearest neighbors, random forest. And well, we were using the root mean square error and the mean absolute error as error metrics. But on the baseline, this was our main competitor, was the average facial soft tissue depth per landmark in a population. We performed different experiments, manually selected landmarks and complete observations. That is, no missing values, the same as the first one, but including observations with less than 5 missing landmarks using imputation. As I said, imputation means to create the values that are missing. Automatic feature selection. So this is like saying, I'm not going to pay much attention to the most important landmarks from the forensic perspective, but I'm going to let the machine select these landmarks. I have to say that this failed quite miserably. And the last one is the same as the second, but including biological profile estimation. And just to give you the take-home message, this was the best strategy, right? So you have to use, at least in our experiments, manually selected landmarks, complete observations, then you can use imputation when you don't have many missing points. And then if you can, you should include biological profile information. Conclusions. The average criterion in our experiments was commonly outperformed by around 10% in both mean absolute error and root mean square error when using machine learning methods. So at least it seems like a good strategy to follow, or at least to try. And the incorporation of sex and body mass index generally improves results around 5–10%. More things. Now I'm going to move, because I think we don't have much time, right? Facial imaging. And this is a very nice picture from, again, I'm going to do publicity here, from our PhD student, Guillermo Gómez Trenado. Very nice PhD dissertation. If you are going to stay here for 2 weeks, my advice, my recommendation is that you attend the defense. So he was working on his PhD on automatic landmark localization, as I was explaining in the first project. And he was working as well on phase aging. Phase aging means that giving an image, and I tell the machine, okay, I want this image to be 75 years old. Okay, do the pertinent transformations in order to try to simulate this age, right? Or text-based editing, that I'm not going to talk about this here, but at least I want you to know what is this. Text-based image editing is like, as Oscar was saying, in artificial intelligence is not an, I mean, it includes many disciplines, right? If you look at any artificial intelligence textbook, you will see robotics, computer vision, natural language processing, representation, knowledge, planning. So in this case, text-based image editing is a task that is solved by vision language models, VLMs, this is a very hot topic nowadays. These are multimodal models that can learn from images and text. So this is like shaking hands between computer vision and natural language processing. And you can see at this example, given an input image, I can say, okay, change the age, and you are going to change the age. Now add a long beard, so it's going to add it. Now add a cap. So this combination of text and video and vision, which is really, really interesting. And even nowadays, if you check a book in computer vision, the last chapters are going to be about this, vision language models, okay? So what we did here was, okay, given an input image, if I tell you, change the age to 60 years old, okay, we are going to modify the image, but we are going to try to have some custom structure preservation. As you can see here, we are forcing to keep the identity closer to the input image. And here, we are not keeping in the same way the identity of the person, and the same happens here. So at this point, with this low custom structure preservation, what we are modifying, what we are doing is modifying more the image at the expense, as I'm saying here, of potentially losing identity. So what is the main intuition behind this approach? We are working with this CASP mask. So our network is predicting this blurring mask that indicates the more age-related regions. So these more age-related regions will be the ones that are more intensely modified to fit the target age. And this degree of modification, this degree of preservation, depends on the user. Well, what's the main structure without entering into any detail? We have an encoder. So the input image is passed through this encoder. We have an internal representation, and we have a decoder conditioned by the target age, and the output, we will have this generated image. And we are training with facial images and their associated age, not images of the same person with different ages. We perform a user study with 80 different users, and just to make a long story short, we won on every one of these sections. We were asking to these 80 people which one, because we were showing the generated images from these three methods. At the time, these two methods were as well part of the state of the art. So which one better depicts a person from the target age group? CASP was the winner by a large margin. Which one better transforms the original picture to the target age group while reasonably maintaining the person's identity? Again, CASP was the preferred strategy, the preferred method by these 80 users, and so on with the other ones. And here, this is my final slide. You can see the input image. These are 4 input images, and these are other approaches at the time of publication of this paper, were competitor methods, and this CASP was our proposal. So, well, I will say that at least in relation with these competitors, qualitatively, we were able to provide a good result. So, I'm done, I guess.
One second. Our extra time is over, so now we are late. It's mainly my fault, so I will take 3 minutes. The very last part, and we have recognized experts in the audience, like Carlos Stefan, is another craniofacial identification approach on comparative radiography. And so the idea is to try to identify a human being using a superimposition of antemortem and postmortem data, and frontal sinus, that is the most related capital structure to craniofacial identification, is supposed to be one of the most individualized in the structure. So here, we again automatize all the approach. It's a similar approach, 3D to D, because you do a 3D model of the bone that is appearing against the radiography, the 2D radiography, but it's much more difficult. Before it was 2 different objects, a skull and a face, and now you have the same object, but you don't have landmarks. So you need to superimpose the surface, the silhouette. So that was more complicated. The whole approach was proposing to do the 3D scanning, and then to automatically segment the structure, in this case, the frontal sinus, and to automatically register it over the 3D model over the 2D image. So the first stage was done using deep learning. And again, we focus on a real world application. So this is not for a paper, we publish it, of course, but we wanted to work with real images, real X-ray images, so 1024 by 1024. And again, we wanted to have a very quick approach, and we had a small number of data, small number of samples. So we needed to add some modified images in order to provide the network with additional information. And it worked, identifying, segmenting the 2 different regions, the region that is visible and the region that is not visible. And the quality was pretty good. There were some small over-cementing regions and under-cementing regions, but in general, the quality was pretty good with some classical measures. And the second stage was, again, very complicated, slow. In some cases, it took as much as an hour. We used an advanced algorithm in order to reduce the runtime. And the other problem was the occlusion. So you need to superimpose a 3D bone that is complete with an X-ray where some parts can be occluded. So we incorporate the occlusion region into the metric that is guiding the approach. And here you can see the iterative approach. And I just have one slide on the validation. This is a real-world validation with real-world data. And you can only see that the manual segmentation and the automatic segmentation got similar result. The manual segmentation is better. But the very good thing is that only identifying using the error of the registration, there is a clear difference between negative and positive cases, identification. And just two final slides. So as I told you, this is a huge work of many people of almost 20 years. We started working within Maleman in January 2005. So we have got so many papers, so many projects. Skeleton ID is our baby. So these guys are working so hard, and many of our methods are implemented there. So it's nice for a researcher to have that. And the most important thing, Pablo has already done it. I didn't do it because of the time, but I always have this final slide where you can see most people that is looking around, and most people we have collaborated with, engineers, computer scientists, forensic anthropologists. So this is not Pablo and my work, but it's the work of all those guys and girls. And thank you so much.